right, so we're going to start off with the bridge assignment, but we're going to do it on a whiteboard and kind of go through it. The information on the bridge assignment was building towards the one reaction that we're doing today. But I want you to keep in mind over the course of today that this one new reaction is just a variation on electrophilic aromatic substitution. So everything we did over the course of the last week is still true for this reaction. But this one reaction is simultaneously more important than the rest, I would say, and also has significant limitations and problems with it. So it's one that we are going to spend an entire day on, even though it's just one reaction. But I would like to go backwards a little bit to things that we have done to build towards the one that we're doing right now. So the first question I asked you guys to answer before class was the issue with carbocation. So here's a carbocation right here. A lot of people remarked on the fact that it's quite unstable. So why is a carbocation unstable?
Because it's a carbon with 3 bonds missing an electron.
Yes, so it's missing electrons. It's really our only cation that doesn't have a full octet. So that's a pretty significant issue. I asked you to go back and kind of think about this reaction in terms of SN1 or E1 reactions. SN1 and E1 reactions might involve something like this, in which you have an alkyl halide, but you don't have a strong nucleophile or a strong base. So the reaction doesn't happen in the concerted mechanism, meaning it doesn't all happen at once. So if you only have a weak nucleophile or a weak base, you basically wait around for the leaving group to leave. In which case we would end up with something like this, which is a carbocation. So in E1 and SN1, which were awful reactions that we really only learned about because we try to really avoid them, but we would get a carbocation as a possible intermediate. One of the big issues with E1 and SN1 is we could get multiple products. So looking at this carbocation, do you remember what could possibly happen to this one, which would give us multiple different products? It's been a while. Yes, so you get a hydride shift, which would look like this, where the hydrogen can hop over there. And in doing so, you would get a different carbocation. We call this rearrangement. So when we went through this last semester, we looked at it in terms of hydride shifts. Truthfully, you can have alkyl shifts as well. These molecules will rearrange themselves in many different ways, but the whole goal is that this is a secondary carbocation, and it could rearrange to become a tertiary carbocation. Why would it do that? Yeah, exactly, to be more stable. So carbocations will rearrange to become more stable if they can. And that was true last October. That is true now in April. That'll be true forever. It doesn't matter how you get a carbocation. If it can rearrange to become more stable, most simply with a hydride shift from one of its carbon neighbors that has a greater substitution pattern, then it will do so. And you largely can't prevent that. And so primary carbocations are awfully unstable, and they'll always rearrange if they can to become secondary or tertiary. And then this is a secondary, which would rearrange to become tertiary. You get a tertiary carbocation. They can't, there's no reason to rearrange. That's as stable as you can get. So one of the big issue with carbocations is that they can rearrange, which in terms of E1 and SN1 would give us multiple different products. But that's true anytime you have a carbocation. So stick that in the back of your head for just a few minutes. All right, so the other thing we were looking at was one of our strong electrophiles that we did last week for electrophilic aromatic substitution was that Cl2AlCl3, so aluminum chloride plus chlorine. And the mechanism for this starts off with the idea that aluminum does not have a full octet. So it's an electrophile, we like more electrons. And one of those chlorines can share electrons with that AlCl3. And so that would give you this kind of funky looking structure that has an Al minus and a Cl plus. And so I circled this Cl plus right here and asked you guys to identify the reactivity of it, which was something that we did a week ago in this class. But a Cl plus does have a full octet, and it does have a plus charge, but it's not an electrophile. So an electrophile is something that wants more electrons to be shared with it. This Cl+, much like an O+ or an N+, it doesn't have enough electrons, but it has too many bonds. It doesn't want more bonds, it wants fewer bonds. So how could this chlorine lose one of its bonds? Would it want to push electrons away from itself or pull them toward itself? Toward itself, right, because it doesn't have enough electrons. So what's the reactivity that we call something that wants to pull electrons toward itself and break a bond and leave? A leaving group. So an O+ is always a leaving group. Cl+ is always a leaving group. And N+ is always going to be a leaving group, because what it wants to do is either this right here, which is to take that bond back to itself, which would make it neutral. But if I did this, it just would go backwards. And so that will happen, but it's largely pointless. The other thing that can happen is it'll pull electrons away from that chlorine right there. And that would make this chlorine neutral. And so this chlorine right here is a really, really, really strong leaving group. And whoever's attached to a leaving group, like this chlorine right here, is a really, really, really strong electrophile. So this is how we started our discussions of electrophilic aromatic substitution, is basically aluminum chloride makes chlorine a better leaving group. And when that whole chunk right there pulls away, we end up with something akin to a Cl+ by itself. So that chlorine right there acts as if it is a Cl+ or a chlorine with no bonds and too few electrons. So this was our very first really, really, really strong electrophile for electrophilic aromatic substitution. It's kind of this chunk right here. So aluminum, again, AlCl3 made one of the chlorines into a better leaving group, which made the other one into an electrophile. Everybody got that? Any questions on that? All right, so for our new reaction, and really this is going to be the nuts and bolts of our brand new reaction for today. We're going to do something almost identical. So aluminum does not have a full octet, and it will pull electrons toward itself from whoever. And whoever has electrons, in this case, would be a chlorine. So instead of starting with Cl2, we're starting with an alkyl chloride, an alkyl halide. And that would make something that looks exactly the same with one difference. We'd still have that plus charge on the aluminum, the negative charge on the aluminum, plus charge on the one chlorine that's making two bonds. And what would be the reactivity of that chlorine right there? It's a Cl+ with two bonds. Same thing. It's once again a leaving group. And so once again, it wants to pull electrons away from its neighbor. It can pull electrons away from this aluminum, breaking that bond, and it would just go backwards. Or it can pull electrons away from this carbon. So essentially this entire thing right here is just one big leaving group. And so once again, the purpose of this AlCl3 is to make the chlorine a better leaving group. We can kind of think about this all at once. It's gonna pull that chlorine, making chlorine into a leaving group. And what we saw when we had a Cl2 is one of the chlorines left, which kind of gave you a Cl+. And here the chlorine is gonna leave, which what does that leave you with for this carbon chunk? What's that? Yep, it's tert-butyl, but if we take that bond away, what would be the charge on this carbon right here? Yeah, plus. So it doesn't give you something that acts like a C+. It's just straight up going to give you a C+, which is a carbocation. And the whole purpose of this, remember, was that benzene is very stable. And so because benzene is very stable, the type of electrophile that will react with it needs to be really, really unstable or really, really reactive. So last week we talked about 5 different electrophiles that were strong enough or fiercely strong that would react with benzene. They were Cl+, Br plus, I plus, nitro, the NO2 plus, and then the SO3. Those were our 5 really strong electrophiles for electrophilic aromatic substitution. What we have done right here is generated our 6th really strong electrophile that can do electrophilic aromatic substitution. So this was a fiercely strong electrophile, and this one right here is a strong electrophile. But it's strong enough for electrophilic aromatic substitution. So this is our 6th strong electrophile that can do electrophilic aromatic substitution. All right, any questions on that? So this, all of the rules that we did last week for electrophilic aromatic substitution remain. You start off with a benzene, electrophilic aromatic substitution, put your file on, and take off. All right, question out there in Zoom? Okay, so let's look at what this thing. I think someone either has their mic on or has a question. You mute yourself unless you have a question, but if you do have a question, please ask.
Yeah, sorry about that. I think I got unmuted by.
Oh, you're good. All right, so this reaction is going to look like this. It's a benzene, for example. And if we start off with, let's just use those things, that tert-butyl chloride and AlCl3. The aluminum chloride turns chlorine into a better leaving group, at which point chlorine is going to leave. And when chlorine leaves that tert-butyl group, we would get a tert-butyl carbocation, which is an electrophile that does electrophilic aromatic substitution. All right, and this is going to look just like when we started off with benzene and we added Cl2 and AlCl3. We said that this stuff right here kind of got together and gave us something that reacted kind of like a Cl plus. And those are our electrophiles. So we just did this one last week and we just took a quiz on it. What is the result of benzene plus Cl2 and AlCl3? Yep. So we would lose a hydrogen and add a chlorine. And we could go through and draw the reactive intermediates and draw through all the mechanism if we needed to. I hope that at this point we don't need to, but you would lose your hydrogen, replace it with a chlorine. So what do you think will happen in this reaction? We'll lose a hydrogen and replace it with what? Tert-butyl group. Perfect. So down here, we lost our hydrogen, replaced it with this chlorine, giving us benzene with a chlorine attached. Up here, we lose our hydrogen, replace it with that new electrophile, which is just a carbocation, and that thing comes in, and you end up with tert-butyl benzene. Ta-da! That's our new reaction for today. There are, like I mentioned, there's quite a few issues or limitations with this specific reaction, but overall, it is still electrophilic aromatic substitution. It follows the exact same rules as electrophilic aromatic substitution. But here's why this reaction is so important. Notice that it's making a new carbon-carbon bond. Making a new carbon-carbon bond is essential for building longer carbon chains and larger molecules. And so this reaction, which has a name, it's named after two chemists, Friedel and Crafts. So this is called Friedel-Crafts alkylation. Is alkylation, obviously, is because you're adding an alkyl group. So that's why it's alkylation. Friedel and Crafts are the name of the two chemists. And so we end up with alkylating a benzene. These two gentlemen gave us another reaction that we'll look at on Monday called Friedel-Crafts acylation. But for now, alkylation is the one reaction we're going to go through today. So by and large, it doesn't have to be tert-butyl, but any R group can be put onto a benzene ring by removing the H through electrophilic aromatic substitution. But do remember that this is just another version of electrophilic aromatic substitution. just like last week. It's electrophilic aromatic substitution. All right, how are we feeling? We can do this? So far, so good? Okay.
Dr. Ring,
Yep.
quick question. So when you have the CL with the tert butyl group attached, and then you have drawn underneath it an isopropyl group, but yet you attach a tert butyl. Why? I guess I'm just confused because it looks like an isopropyl, but yet you're attaching a tert butyl.
All right, so keep in mind how many carbons we have. So the tert butyl group is 4 carbons. And when that chlorine falls off right there, it should still have 4 carbons. So what it becomes here is still 4 carbons, just a plus charge in the middle. So this would be an isopropyl group if that carbon was missing right there, but it's still just 4 carbons with the plus charge in the middle. If I had drawn it this way, would it have looked better?
Oh, I gotcha. I can see. Makes sense now. Thank you.
Yeah, it kind of fans out when it doesn't have the chlorine on there, but yeah, okay, good. It's the same number of carbons. It's the same little chunk. It does look weird in that case, but yeah, good question.
Thank you.
All right, so this is Friedel-Crafts alkylation, and we can attach an alkyl group to a benzene ring. So let's go through these limitations one at a time. I'm going to erase this stuff down here. That was our reaction from last week that was similar to this one. All right, so we have 3 limitations / issues with Friedel-Crafts alkylation. All right, the first one has to do with the fact that you are making a carbocation. And a carbocation, while it is a strong electrophile, is not as fiercely strong of an electrophile as something like a Br plus or a Cl plus or an I plus. Those things that we did last week are ridiculously strong electrophiles, and they will react with benzene no matter what the benzene is attached to. Friedel-Crafts alkylation, because your alkyl carbocation is not as strong of an electrophile, it will still work with benzene, and it'll still work with an activated benzene, but it absolutely will not work with a deactivated benzene. So it will not work with a benzene that has a deactivating group attached. All right, pop quiz. What were our deactivating groups? So you might remember this. This had to do with when we're talking about ortho-para versus meta substitution or meta directing groups. So let's start with our activating groups. What were our activating groups? The ones that were ortho-para directing. Yep. So the most activating groups were those that had lone pairs. And so we went through and spent a lot of time drawing the resonance structures. But the main deal is that in the electrophilic aromatic substitution reaction, the benzene ring is sharing electrons out to an electrophile. And so something with lone pairs is conjugated to the benzene ring and can share electrons into the ring and basically makes the ring more electron rich. The second category of activating groups was R groups. We know that carbons share electrons. So the deal was that once again, they would share electrons into the ring, making your benzene ring more electron rich. And so it's easier for it to share electrons. So those activating groups make this reaction happen faster and more easily because the ring has more electrons to share. So that's activating groups. So benzene rings would work great for Friedel-Crafts alkylation. Activated groups would work even better. However, what were our deactivating groups? It was everything else. It was the middle column.
Your halogens?
Yeah, halogens. So halogens do have lone pairs, but let's imagine like bromine. But we know that halogens are very electronegative, and they actually pull electrons away from the ring. So all of those deactivating groups, sometimes we call those electron withdrawing. Because they're all stuff that pulls electrons toward themselves. And if this happens, then it's pulling electrons out of the ring, which makes that benzene ring somewhat more electron poor. And therefore, it's harder for that ring to share electrons with someone else. And so we find that with benzene, this reaction works fine. But if you start off with bromobenzene or nitrobenzene or something like that, where it has one of those deactivating electron withdrawing groups, then the benzene ring just doesn't have enough electrons and it's unwilling to share them with the carbocation. So it slows this reaction down to the point that it actually won't even happen. None of that is true for last week's reactions. So remember that like a nitrobenzene would still react with AlCl3 and Cl2. It would just be meta-directing. Well, it turns out that if you tried to use these reagents, just nothing would happen. So the kind of that second group was if you had carbonyls. Well, once again, those carbonyls are losing electrons, so they're pulling electrons out of the ring, so they are electron withdrawing. And the last group was really positive charges. And once again, a positive charge would try to pull electrons toward itself since it doesn't have enough electrons. But this was kind of the middle column and then the fourth column, second to the right, and then all the way to the right. All of those meta-directing groups and the halogens, which are orthopaired, but also deactivating, they all pull electrons toward themselves. And so what that means is if you have any of these things attached and you try to do Friedel-Crafts alkylation, it just straight up won't work. So if we were to start with benzoic acid, which is a deactivating group, a benzene ring with a carboxylic acid. This is meta-directing. And deactivating. And you were to add this tert-butyl chloride and aluminum chloride, then nothing would happen. You would get no reaction whatsoever because this deactivating ring has not enough electron density to share with a C+, and so it just won't, and you would just get no reaction. So if you heated this up and tried to get it to work, you would just end up with benzoic acid and tert-butyl chloride and aluminum chloride because nothing would happen. So you can never do meta-directing anything for Friedel-Crafts alkylation because all the meta-directing groups are deactivating, meaning that the ring just won't have enough electrons and it's unwilling to react with an alkyl carbocation. So no reaction whatsoever. So a lot of the reactions we did last week can't work with Friedel-Crafts alkylation. It's just not strong enough of an electrophile to make it go. Does that make sense? Okay, so that is issue number one. So there is, like I mentioned, a lot more nuance to this reaction and a lot more limitations, but it's still a really important reaction. All right, issue two, and I want you guys to see if you can work this one out. If we start off with benzene once again, and benzene does not have a deactivating group, so it'll work fine. And let's say that I'm going to use chloropentane, AlCl3. So once again, the mechanism of this is that aluminum would make a new bond to chlorine, which makes chlorine a better leaving group. And so chlorine would leave. So if you will, take a minute and draw what carbocation would result from that little reaction right there. Not the overall product of the reaction, just AlCl3 plus 1 chloropentane. Which electrophile or carbocation would you get? Okay, so that's what it looks like. But think back to what we did at the very beginning. So that's a carbocation. It is. It is, perfect. So at first glance, it would seem that we are just pulling the chlorine off of that carbon number 1, and carbon number 1 would get a positive charge, which does make sense. However, where we started our class today was that no matter how you make a carbocation, if a carbocation has a more substituted neighbor, it will or could rearrange. With primary carbocations, if they can rearrange, they always will, because primary carbocations are ridiculously unstable. So you see that that carbocation there is at a primary carbon, and its neighbor is secondary. So absolutely, you will get 100% of the time a hydrogen shifting over. And so we would get our cation actually at carbon number 2, and you would end up with none of that. And so as the result of this little reaction right here, this is the carbocation you would get, and this is the carbocation that would react with your benzene. So we will attach a 5-carbon chunk onto our benzene ring, but we're not going to attach it at carbon number 1 because carbon number 1 can't support a carbocation. Instead, it rearranges to carbon number 2. And so that carbon number 2 is where we would attach it to the benzene ring. So the product of this reaction will have a 5-carbon chunk attached to a benzene ring, but it would look like this, where carbon number 2 of that chunk right there is the one that's attached, because carbon number 2 is your plus charge, so carbon number 2 is your electron. So this looks, it's a little bit different than just whatever your R group is, we'll just straight up attach. You have to be a little bit more judicious and draw out your carbocation and see if it can rearrange using the same rules we did last semester for carbocations, which is that they will rearrange to go from primary to secondary, or from secondary to tertiary, or from primary to tertiary. When we did this one initially with your tert-butyl chloride, and we got this carbocation, that carbon right there is tertiary, and all of its neighbors are primary. So rearranging would only make it less stable, so it would never rearrange. So this is an example of one that would not rearrange. And what we just drew is an example of one that would rearrange. So you have to be careful and work through this, but really, if it's gonna be primary, it's almost certainly gonna rearrange. If it's secondary, look to see if there's a tertiary neighbor. And if it's tertiary, it would just never rearrange. So kind of a limitation or issue number 2 with Friedel-Crafts alkylation is that your intermediate carbocations may rearrange. They don't always rearrange, but a lot of times they will. So we just have to be careful. We have to take our time to draw them out and see if they can become more stable. All right, so all of that is kind of, again, based on stuff that we've done already, but is in a new context, so it's worth drawing attention to. Questions in Zoom on that whatsoever? All right, so once again, let's see if we can work through this one. Well, here's our issue number 3. I'm going to start with benzene. We are going to add isopropyl chloride, just those 3 little carbons with chlorine attached, AlCl3. So once again, the purpose of aluminum chloride is that it makes that chlorine attach, and so it becomes a better leaving group, and then that chlorine will leave. And you would get from all of that a little 3-carbon chunk with the plus charge in the middle. All right, first question, can this thing rearrange, or would this thing rearrange? No, correct. It's a secondary carbocation, its neighbors are primary, so it can't get more stable than that. So we would get the resulting carbocation, or that carbocation would be your electrophile, and we would get the substitution of losing a hydrogen and gaining an isopropyl group. All right, does that make sense? This is just the reaction we're doing right now. This is Friedel-Crafts alkylation. All right, so this seems really weird, but this is what would happen if you added one molecule to this and one molecule of that. But we never just add one molecule. We couldn't do that if we tried. So we're putting a bunch of these in together. They don't all react at the same time. So let's imagine that instead of one of those, I've got 100 of these and 100 of those, and I react them together. You can write these numbers down if you want to. You don't have to. We're getting to a point. I'd rather if you kind of follow along and see if you can see what's happening here. So we start with 100 of those and 100 of those, and we start with 0 of these, of course. Halfway through the reaction, we would have reacted 50 of those. So 50 of those would be gone with 50 of these. And how many of these would we have? So if 50 benzenes and 50 isopropyl chlorides reacted, how many isopropyl benzenes would we get? Yeah, 50. So this is kind of like an ICE table. But we would have 50 leftover benzenes and 50 leftover those guys, which is your electrophile. And we would now have 50 isopropyl benzenes. We intend this to be our starting material, and we intend this to be our product. But put yourselves in the shoes of the 51st electrophile. You're in a pot. You've got 50 benzenes and 50 isopropyl benzenes. What would you rather react with? Let's go back in time about 15 minutes. Benzene is benzene, but when there's a group attached, our groups are activating for electrophilic aromatic substitution. It shares electrons into the ring, and so this ring is more electron rich and more willing to do electrophilic aromatic substitution. So therefore, where's this electrophile more likely to go? On that one or on this one? On the product, yeah. So in Friedel-Crafts alkylation, we are adding an alkyl group. And when we add an alkyl group, that means that our product is more likely to do electrophilic aromatic substitution than our original starting material is. And this creates some issues for us because you will not necessarily end up with all of your benzenes being alkylated, because at a certain point, your electrophiles will start reacting with your product and giving you diisopropyl benzenes or triisopropyl benzenes, and give you a mixture of those guys and then a bunch of unreacted leftover benzenes. So every time you add an alkyl group, you make the product more reactive for electrophilic aromatic substitution than your starting material was in the first place. This is something we didn't have to think about last week, because if you think about those 5 electrophiles we used last week, chlorine, bromine, and iodine, when you put them on a benzene ring, they're all deactivated. So the product last week would be less reactive than the starting material, so this was not an issue. A nitro is also deactivating, so when we put it on there, it made the product less likely to react than the starting material, so this was not an issue. A sulfonyl, which is a sulfur with a bunch of electrons being pulled away, is also deactivating. So everything we added last week would make your product less reactive. And therefore, we didn't really have to worry about di-substituted or tri-substituted products. But when you do Friedel-Crafts alkylation, you're adding an activating group, which makes your product inherently more likely to react than your starting material, which is a pretty big issue. So I'm going to write this rule down, and then we'll talk about how we can get around it. All right, so our product, which is an alkyl benzene, is more reactive in EAS than your intended, whatever it was, starting material. And so di-substituted or tri-substituted products are possible. and indeed likely. So that is a new issue that we have to deal with and worry about now. All right, so let me show you how we can get around this and why really this is something that we can kind of avoid. So I'm going to change my numbers a little bit. Let's still say that we started with 100 of these. So after one of these reacts, we'll have 99 leftover benzenes. We'll have 99 leftover electrophiles. And we'll only have one of these products. All right. Everybody follow? So this is like right after just one of them reacts. So looking at this electrophile, what's it more likely to react with, do you think? The 99 benzenes or the one isopropyl benzene? Yeah, so technically, the isopropyl benzene would be more reactive, but it's a pretty strong electrophile, and you got 99 of these. So you're more likely to bump into what they have a lot more of, even if it's less reactive. So what we can do to get around this issue is that instead of adding a 1-to-1 stoichiometric ratio of these things, we could add maybe let's say we add 10 to 1 or 1,000 to 100. So now after half of these guys react, you'll have 50 of those left over. You'll have 50 of those, but you still have 950 of those. So if we make sure that our starting material aromatic ring is in vast molar excess, then you're always going to be more likely to react with your intended starting material and less likely to react with our product. So if we screw around with our stoichiometry and make sure that our alkyl halide is your limiting reagent, then just based on probability, yes, this is more reactive than that, but you'll notice that I basically have, I don't know, like 20 times as much benzene. So it's just more likely to bump into benzene, which means you're much more likely to just get the mono-substituted product. And so this is always something we can try to do. It can create insurmountable issues if, let's say, instead of benzene we can just buy in a bottle, no big deal. But a lot of pharmaceutical reactions in which they're making drug molecules, small molecule drug molecules, a lot of times they might be 10 steps. And if this is step number 9, then you might have spent a couple months making your aromatic ring, and you don't want to just toss a bunch of it in here just to waste. And so this can be a big issue. But if you just start with benzene, we can just play around with our stoichiometry and kind of avoid this issue. This is not something that is going to impact your quizzes whatsoever. I'm just always going to ask you to just go ahead and give me the mono-substituted product. But I want you to be aware that this is an issue that we have to worry about and think about practically because of the fact that we've made an activated product. And so while this is our product, it's actually a pretty great starting material for more electrophilic aromatic substitution. All right, so this is Friedel-Crafts alkylation, and I've just added a whole bunch of nuance to it. But do remember that this is still electrophilic aromatic substitution. All right, any questions? Otherwise, we're just going to do some examples. Just look around at everybody in the classroom. All right, no questions from anybody? Okay. All right, so let's do some examples here. So let's say I start off with ethoxybenzene. And I'm going to add isobutyl chloride and aluminum chloride. All right, so first off, react these two things together and look at your resulting intermediate carbocation, and then react it with this molecule right here, which has an oxygen attached to your benzene. I'll give you 2 or 3 minutes to do this. If you have any questions, please just ask. Do you remember how this directs the next reaction? Yes, you would get this. That absolutely is not going to be the file. So you're going to do electric filter and substitution. Well, so on Wednesday, on those, the groups that are on there already direct there. All right, so the aluminum chloride would react with your alkyl chloride. It would bond onto the chlorine, making the chlorine a better leaving group, and the chlorine would leave, which kind of looks like it would give you this carbocation right here. But this carbocation is primary and it has a neighbor that's tertiary. So this would always rearrange to give you that tert-butyl carbocation. So it turns out that for this reaction, it's going to give you the exact same thing as if you were to add the tert-butyl chloride in the first place, because both of them would have the chlorine leave and just give you this thing here. So this would go straight to that. This would take a roundabout route, but this is going to be your electrophile as a tert-butyl carbocation. All right, so looking at our starting material, it might look like we're doing something new and crazy, but this is just exactly what we did last Monday or this past Monday. If you have an oxygen on your benzene ring, it is activating and it is ortho-para directing for electrophilic aromatic substitution. So these are the ortho positions right next to the oxygen, and this is the para position. So this doesn't change your reaction, it just directs where it's going to occur. And so we're going to take a hydrogen off of our ortho position and put on the tert-butyl group, and we're going to take a hydrogen off of the para position. You'll just get one or the other. All right, so we would get that guy. This is the para substituted product. And we would get this guy, which is the ortho substituted product. And remember, just like on the quiz on Wednesday, if you've got an ortho para directing group, you need to draw both the ortho product and the para product because you'll get a mixture of both. We'll never end up with meta substitution or meta directing working on this because all of the meta directing groups are all electron withdrawing, so they're deactivating, and then Friedel-Crafts alkylation wouldn't happen. So this is what we would get from this. All right, any questions out there in Zoom or here? You okay about that? All right. I don't want to get too cheeky, but if we were to start with this and added all right, someone stop me. Yeah, so nitro is a deactivating group. So no reaction. So you don't even need to worry about it. Nothing will happen. AKA. Okay, so you don't even need to worry about this. All right, let's do. So we're going to start off with, instead of just benzene, start off with an amide here. All right, so I'll give you a couple minutes to get a head start on this one, see how far you can get. That's it. Where do you kind of have okay. You're on it, though. One of them is activated. Let's see that. There you go. Right. So this is a partial positive chart. Cardinal are all. And then a partial positive. You find this? And that has lone pairs. And then lone pairs. All right, so once again, the aluminum chloride serves to make chlorine a better leaving group, and then the chlorine will leave. Just glancing at this real quick, it looks like it would give you a carbocation on carbon number 1 of that 5-carbon chunk, but that would be primary and its neighbor is secondary. So you wouldn't actually get any of that. It would straight up rearrange to give you this thing, which is a pentane with a carbocation at carbon number 2. Right, and then we have to look at these 2 rings and see which one is more likely to react. The nitrogen has a lone pair. Remember that anything with a lone pair, whether it's oxygen or nitrogen, those are all going to be ortho-para-directing. And besides halogens, they're all going to be activating as well. So this ring would be activated and nitrogen is ortho-para-directing. So it would want the reaction to happen there, ortho, and there, para. A carbonyl is electron withdrawing. There's a partial positive on that carbon, partial negative on the oxygen, but it's the carbon is what's right next to the ring here. So this is deactivating and meta-directing. So you would not react on the benzene ring over there. So this ring is deactivating because it's attached to a deactivated group. This ring is activated because it's attached to a nitrogen. So this is where your reaction will happen. And we will be attaching a 5-carbon chunk at carbon number 2 to the ortho position, and then also to the para position of this guy. So this is going to take a minute to draw it all out because it's pretty big. That's what I get for giving you complicated examples. But NH, carbonyl, and another benzene over there. And we would get, so this is 1, 2, 3, 4, 5. So notice that this is your same little 5-carbon chunk that we had right here, but we're attaching it at carbon number 2 instead of carbon number 1. So we would get this, which is the ortho substituted product. And we would get this, which is the para substituted product. Again, it's got that 5-carbon chunk, but it's attached at carbon number 2 instead of carbon number 1. All right, That's probably as complicated of an example as I can make for you. Kind of wraps in most of our limitations. Again, that it will never happen on a deactivated group, and that rearrangement can occur if you have a neighbor that is more substitute. All right, so for these reactions, we're gonna have to do them backwards as well. So if I were to start with, let's say, aniline, and I wanted to make two. This would be sec-butyl aniline. What reagent would I need to add? All right, so Letitia, what would my reagent look like for this? Yep. Yep, so it's this 4-carbon chain, and where would the chlorine be? Okay, great. So in this case, it actually doesn't matter, because if you put it on the end, it would rearrange to the second anyway. But this probably makes the most sense. You would have 2-chlorobutane, and that would give you a butane attached at number 2 on the benzene ring. And then, of course, to make that chlorine a better leaving group, you would add that aluminum chloride. Perfect. Any questions in Zoom about that one? Does that make sense?
So for all of these reagents, we've been adding chlorine. Could you hypothetically put like a bromine on there and just do FeBr3 as well?
Yep.
Okay, cool.
Yep. It turns out that usually the chlorine versions are cheaper. And so since it doesn't matter because it's just a leaving group that's leaving anyway, we tend to do this with aluminum chloride. It's the same thing is true of, all right, sorry for this. You can ignore this if you want to. We've been using mostly acid chlorides in class. It turns out that that's what we use more commonly. We're not using those right now, but acid bromides do the same thing, and they exist, and we make them kind of the same way. But just because they kind of exist for the leaving group to leave, so it kind of doesn't really matter which leaving group you use in the first place. But yeah, you could do it with bromine if you wanted to, and it should work just fine.
Thank you.
All right, so Chloe, I'm going to give you a question that doesn't have a good answer. I just want you to tell me why it can't. So if I were to start with benzene and I wanted to make hexylbenzene, tell me why this reaction just can't work. Yeah, it would attach at the wrong carbon. So kind of looking at what we've got here, we should be trying to add a 6-carbon chunk, but you would want to attach it at one of the very, very end carbons. But if you added this reagent set, it actually wouldn't do that because it would make that leaving group leave. But this thing would rearrange and you would get none of it. So you actually wouldn't be able to get that product. So Friedel-Crafts alkylation will never, ever, ever give you a longer chain than 2. So we could do it with a 2-carbon chunk because there is no rearrangement that could happen. But for 3 or 4 or 5 or 6 or any number like that, you can't attach a straight chain because it would always end up rearranging. So this is impossible to make through Friedel-Crafts alkylation. And so this is something that we will be able to make, but kind of Friedel and Kraft went back to the drawing board and came up with another way of doing this. And that's what we'll talk about on Monday with Friedel-Crafts acylation. is it gives us some different options. All right. So that's it. You guys have a free 5 minutes today, unless anybody has any questions on this stuff. Okay. Thanks. Remember, we do not have lab on Monday or Tuesday of next week. Your experiment, 5 out of class stuff is due tonight at midnight. But thank you very much. And I will see you all in the next week or two. Next Friday is our last in-person class. All right. Talk to you later.